our distinguished guests, esteemed colleagues and fellow learners. It is with immense pleasure that I stand before you today to express our heartfelt gratitude to our esteemed resource person Dr. B. Narasimhan for their valuable contribution to this international conference. Thank you, sir. Dr. B. Narasimhan's insight to machine learning and the data science have been nothing short of illuminating, and the presentation was not only packed with the knowledge but also delivered with such clarity and the engaging fashion that everyone in this room was captivated. Isn't it? It is in a very engaging fashion to deliver this. Very thank you, sir. The responses to our questions are also thoughtful and insightful and challenging us to think deeper and explore new perspectives. On the behalf of our college and the department, we want to express our deepest gratitude for your willingness to share your expertise and passion with us. Your generosity of spirit and dedication to computer science field are truly inspiring, sir. So please join me in giving a round of applause to Dr. Narasimhan, Assistant Professor, Department of Computer Science, Nehru Arts and Science College, Coimbatore, for our guiding light to this incredible journey of learning and exploration. Thank you.
Thank you, dear ma'am, for joining us.
Welcome back, everyone. We hope you had a rejuvenating tea break and you are ready for the exciting session lined up for the rest of the day. Please take your seats and let's continue the journey of exploration and knowledge sharing. We have more insightful discussions ahead, so let's make the most of the remaining sessions. Thank you for being back on time, and let's dive back into the conference. And a kind reminder that it will be appreciated if you take a moment to switch your phones into silent mode for an uninterrupted surrounding for the speaker as well as the fellow attendees. Thank you. Department of Mathematics, nurtured since the inception of MES Kalladi College in 1967. The Department of Mathematics has been an integral part of the institution's journey. Initially offering a pre-degree course, it expanded its educational horizon with the introduction of complementary papers in mathematics for BSc Chemistry and BSc Physics courses. The pivotal moment arrived in 1971 when the university sanctioned the BSc Mathematics course with Statistics and Physics and complementary course. Evolving with times, the department elevated its status to a postgraduate department in 1995, boasting two accomplished research guides. With a keen focus on transformation, we aspire transition into a dedicated research department. Our faculty, characterized by both qualification and experience, forms the backbone of the department, complemented by a well-equipped library.
It is an honor to introduce our esteemed speaker, Dr. Santosh George, Professor at the Department of Mathematical and Computational Sciences, National Institute of Technology, Surat, Karnataka. Dr. Santosh George would definitely bring a wealth of knowledge and expertise, and today he will be sharing his thoughts about the highly interested area. It is with great pleasure that we invite our esteemed session chair, Dr. Girish KP, Assistant Professor and Head of the Department of Mathematics at MES Kalladi College, Mannarkkad, to join us on stage. Dr. Girish's expertise in the field adds a valuable perspective to our discussions, and we are honored to have his guidance throughout the upcoming session. Please join me in welcoming Girish sir to the stage. Sir, please.
Good morning, everyone. I am honored to be here as the chair of this esteemed session on convergence analysis of iterative methods for nonlinear equations. I would like to introduce our speaker, Dr. Santosh George, who is a professor in the Department of Mathematics and Computational Sciences at National Institute of Technology, Karnataka. He focused on the area of research, functional analysis and applied mathematics with expertise in fixed point theory, convex optimization, ill-posed operator equations, constructive approximation, etc. He also one of our proud alumni, having studied his pre-degree and BSc here from 1982 to 1987. He completed his MSc from Calicut University campus and his PhD from Goa University. He has more than 400 national and international publications with good impact factors. He has supervised 12 PhD students and is currently mentoring 5 more students. He has 1,244 citations, which are H index 18 and I-10 index 34. He had received 2 awards, the Faculty Research Award and Chef's Grand ICM 2022. He has delivered several invited talks at reputed mathematical institutes in different parts of our country and abroad. I would like to invite our most respected and lovable GK sir for the welcome speech. Thank you.
Respected Chief Guest, Dr. Santosh George, Chair, Dr. Girish, Head of the Department of Mathematics, Mr. Saidalavi, and other faculty of the Department of Mathematics, faculties of other departments, students, other guests, a warm morning to all of you. I'm very happy to stand before you to welcome Dr. Santosh George because he was my classmate. We have studied B.Ed course in 1990 in Calicut University. Before that, actually, I have, in companion with Dr. Santosh George in 1987 even, first I joined for my MSc course in Calicut University. At that time, he was also a student in Calicut University, but my parents was not ready to put me in hostel. That is why I changed from Calicut University to Kerala Varma College. Otherwise, we would have been classmates even in MSc course as well. And at the same time, Dr. Girish introduced him as the alumni of this college. We both are alumni of this college. He is a student alumni, I am a teacher alumni. That is the only difference. The last 26 years, I have spent only 2 years in between. I was in Asmabi College. All other 24 years, I had been worked in this prestigious institution. Now, just I retired in this last May 2023. But during this 6 or 7 months, I'm seeing a drastic change in the environment of this college. I'm very happy to see this most beautiful seminar hall of this college. After this session, I want to just roam in the campus of this prestigious college. I want to see what are the changes going on in this college. Because at present, I am working as a principal in Lakshmi Narayan Arts and Science College, Mayanur. That is a very small college, only 450 students, and that college started only in 2017. Now we are in a very infancy period. We are stepping forward, and I want to see the changes here. That changes I can. It will be a motivation to me to introduce these are the changes that is going on around in my parent college, and I'll talk to the management, and I can make some changes in the my college at present as well. Okay, anyway, Dr. Santosh George is a very eminent personality. Dr. Girish introduced his academic achievements, all this here very elaborately. I think he has completed his PhD in Tamban Nair. Dr. Tamban Nair was his guide, I think. But one thing I want to convey here, I told you, I am the principal of Lakshmi Narayan Arts and Science College. But I joined just 2 months back. That is in last October I joined here. But very sad to say that we de-affiliated BSc Mathematics from the college because the last year no student was turned to join in BSc Mathematics. That is not only the case of the Lakshmi Narayana College, but you can see all over Kerala. No one is ready to study BSc Mathematics, BSc Physics, BSc Chemistry. Last year in my college, they got sanction to affiliation to start BSc Physics. But they didn't start the course even. No one is ready. No student is ready to study the science courses. I don't know why. We are all saying that mathematics is the queen of all sciences and that is a most beautiful subject. All these things we know, those who are in the field know very well, very nicely. But others are not knowing about it. What is the reason? We have to think about this. We are always thinking about big things and we are thinking about the research fields and what are the changes going on. We are always saying that mathematics and science controls the whole world and all. But the young generation is not ready to turn to this field. All those persons or we people who are immersed in this field of science should think about it, and we have to make some arrangements to attract the young generation to these prestigious fields. I'm not going to elaborate all these speeches and all because this is a session only for 1 hour. Dr. Santosh George is ready to with the slides and all to talk about his presentation and all. But anyway, I'm very thankful to the organizers to invite me to come to this prestigious session. And anyway, first of all, I would like to thank all the participants and all this for giving me a chance to stand before you. Anyway, my official duty is to invite my fellow student, Dr. Santosh George, to present this session. On behalf of all, I heartily welcome Dr. Santosh George to come over here and present his session. Thank you.
A very good morning to all of you. I thank Dr. Girish for the nice introduction. Of course, Goa Lakshman, and actually I want to thank the organizers, but I realize that it's a big group of organizers because I'm afraid that I'll miss some names, so I just thank, of course, Madam is here and others, because I don't want to miss any names, because anyway I thank. Of course, it is a nice thing for me to say homecoming. Actually, it's a homecoming to the institute. I have been here a few years back when Gopalakrishnan was there. Once I gave a talk, and during COVID time also, I think I did on online. I think some STD or something I talked about it. Of course, being a mathematician, I think it is always better to have a chalk and duster. So that's our great, because even though there is a modernity there, normally we don't like, because it should come naturally from your mind. So when you are teaching also, and maths if you want to do, you have to do it. You cannot look at something and you do it. I don't project normally. Even during the entire COVID time, people were trying to make the slides and present it. I used to go to my department with a small camera. I take all my lectures in the board, and then I used to send it, because the students has to, when they listen, they have to take down. If I give them note, They think it is there. It's there in the book, but you won't learn it. So you have to work hard. Of course, moving to this topic, since I realized that the audience is a mixed group, not mathematicians, of course, I hope that you can hear me with something in hand. That is again going to cut my flow. Okay, so mostly anyway, without some equations and all, we cannot talk maths. But I try to avoid all the jargon of the proof. Let me see what best I can do. So this is something which, when you try to solve any problem in life, what will happen? You try to model it, right? Yeah, if you have a problem like that, I'm more comfortable because I don't like to fix in one place and talk. I'm not a speaker in that way. I basically like to be. Okay, so when we I hope I'm audible. Okay. So when we try to model a given problem, normally it gives an equation of the form. Of course, my talk basically is structured like this. So when you try to model, this is going to be an equation of the form f of x is 0. So for the time being, f is from a Banach space to a convex subset, open convex subset of a Banach space to itself. Okay. So when we talk about, we say that it is a model. So immediately people will ask, where is an example? So let me start with an example of a problem where you have a set of pipes through that a fluid or a gas is passing, and this cooling system is there, and you want to find the friction inside. So let me start with an example. Okay, I have to go here, right? So you look at the pipe friction problem. It's where you want to study how much resistance in the channel when a gas or a water is passing through a pipe with a cooling system. So then let's say, of course, physics people are there. Colebrook equations, so they call it this Colebrook equations. That equation is like so how to calculate the friction factor F. So the friction factor F is going to satisfy this equation. 1 by root of F plus 2 log epsilon 3.b plus 2.51 root F. And don't ask me what is this 3.5, 2.5, etc. That's the physics bureau because it's modeled by them. They may have various factors involved in that. So where B is the diameter of the pipe and R is the Reynolds number and rho is the density of the fluid and B is velocity. So if you look at it in mathematician's way, so we will say that this guy wants to solve the equation f of x is 0. I completely forgot about all what is happening in this equation. I will say I have an equation f of x is 0. What is f of x? That I will define, that is like this. So then I don't want to solve this only. What mathematicians try to do, that's why normally we will say, when we talk about a mathematician, say that if you ask a mathematician to shoot an elephant, he knows only how to shoot a black elephant. If you give him something gray, what he will do, he will find first to paint the elephant into black, then he will shoot, because he knows only that. So that's the basic idea. You try to do something, once you know something, any problem is given, you convert it into something which you know, then you attack it. So that's the basic idea. So instead of solving this, I want to solve something more, f of x is 0. So then, the problem with this, the moment it is a non-linear, of course this is a very non-linear equation, you have already seen, it is non-linear, no way it is linear. So if it is a linear equation, very often you have a exact solution is available. But in the case of a non-linear equation, you don't have a solution, regular solution, you cannot get it. So then, what we can do? You have to find an approximation for a solution. How to approximate a solution? So that means normally you look for an iterative method. You start with somewhere and you want to reach there. So then, you will see that how many iterative, there are so many different iterative methods are there involved. he has classified them based on the requirement of that equation. So first we can look at one point iterative function. That means an equation of the form. We find xn plus 1 is phi of xn. Phi is an iterative function and xn is the previous iterate. Then for example, so if again you can see that abstractions. So you ask me this, what it is, you find this. But you look at an example. So best example is Newton's example. So Newton's equation most of you are familiar with. Xn plus 1 is xn minus f of xn. F dash of xn inverse into f of xn, or if you are in an Rn and all, you can write like this. Okay. So here you can see that phi is nothing but the phi of xn is the right hand side. So this type of iterative methods is called one point iterative function, because you are using previous iteration only to find the next one. So next one is that sometime you will have it with memory. Means you want to use the previous one or two iterate to find the next iteration. That means when you write a program, you have to keep a slot for its memory. It has to keep the previous one. Okay. So earlier on, if you write, you don't have to worry about it. It will just in a loop it will work. But here you have to keep the previous memory. So that means in the case of iteration, it is going to, depending on someday 1 or 2 or up to k previous iterates. So for example, for this is a secant method. So secant method, you can see it is of this form xn plus 1 is xn minus x minus xn minus f of xn minus s. If you rewrite it as one by that, you can see that it's nothing derivative. It's an approximation for a derivative. F of xn minus f of xn minus y, xn minus xn minus s. Approximation. So why the secant method? Because you see very often the functions which you are trying to approximate do not have a derivative, so that you cannot think about it. So therefore, we could come up with a method called the secant method. So then there is a multi-point iteration. So multi-point iteration is it is not only the previous iterate, the previous functions of the previous iterate is used to put it into the equation to get it. Okay, so this is an equation of this form. Where an example for this is, you can see that Newton goes where you can see where you can A is going to be a function f dash of un minus vn. Un is again xn plus yn, the average of this, and xn minus yn. So if you put that, then it is you will get a multi-point. There are various points, multiple points are there, and you are using functions of the previous iterate distribution. So then again you have multi-point with memory. There it's not only previous thing, you have to keep a memory for the previous iterate. So this method is of this form, where incidence phi is depending on previous n minus q or functions of previous iterates. Each of incidence is going to be a functions of some functions of wn. So example for this is the twin graph family of methods. You can see it's again. People wonder how these people are getting all these iterative methods. So that's a very interesting way. When you study, you always try to find a base. Then next question is that, of course, once you have various type of iterative methods, then naturally people will ask, so many which one I should use? So I have so many iterative methods now. So it's not only if you look at the history, so many iterative methods that nowadays, even the yesterday also I have a new methods and text published recently. So each time then people are getting the iterative method. So now, if you look at the Newton's method, if somebody say no, I don't want to use this fractional derivative because f dash of xn inverse you want to find every time. So that's a problem. You have to find the iteration and the corresponding f dash is nothing but a Jacobian. If you look at it, it's a Jacobian of the function, it's a matrix, and each time you have to find that matrix and its inverse. And it's too much of computation is there. So can I reduce that additional computation? So then they come with the method here, say 2.3, they fix the derivative at one point. Then it's called a modified Newton's method. so then the question comes. So now I have so many iterative methods. How can I use, which one I should use? There should be some sort of measure, some sort of control we must have. Then only I can say, yes, this method is better than that, or that method is better. So then, to come up with the first, I think it is Cobb and Ortega. They have the, something called order of convergence. Order of convergence means speed at which it will converge. Okay. Anything in a high speed, you need something, it should be fast enough. So how to measure the speed of the convergence? So for that, they have defined what is called the order of convergence. So order of convergence of a sequence xn, which converges to some x star. X star is a solution, nothing but f of x star is 0. So it is defined like this. Limit of n goes to infinity norm of xn plus 1 minus x star divided by xn minus x star raised to p should be equal to a constant. That constant should not be equal to 0. Then we call the Cp the asymptotic error constant or the rate of convergence. Okay, so what they used to do is that if you want to find the equations, order of convergence of an iterative method, basically what they are doing is that you consider the difference between n different and solution xn minus x star as En. So then they use some Taylor series expansion or some sort of expansion and write En plus 1 some k times En raised to p and order of En raised to p plus 1. Okay, so this equation they call, this is called the error equation. So basically the people who are doing research so far is an iterative method is there, they try to find the error equation and then he says it's of order p. But there is a problem, I tell you, that's my recent area of work is there. So actually it is not my area, basically my area of study started with very hard imposed equations. So imposed equation means f of x is y doesn't have a solution in the usual sense, but I want to solve it. So that's what is happening because you remember that the only mathematician who got a Nobel Prize in medicine is the one who worked with the imposed equation. The imposed equation is, for example, f of x is y and you don't have a solution but you want to solve it. How to solve it? For example, if you take a simple matrix 1, 1, 1, f of x, a of x is equal to y is 1, 2 is given. How to solve it? But you have to solve because what happens when you try to model something, you will have an error. So what measurement you are getting is always going to be something like this, then how to solve it? At least if I don't have a solution, I want something near to the solution. Okay. So that is the area I start working initially with the linear operators. So then I worked on something called Hilbert scales. It's much more difficult to some people who know MESKC maybe know the Sobolev space. This is a generalized version of Sobolev space. So then I shifted to non-linear imposed equations. And there also I did something. Then after that I went from the fractions and all these things. So last few years, this may be very recent, 2 years, I will tell you later on what is happening. So basically all the research papers we should try to do is for iterative equations, so they try to find this error equations. So that is the problem. I was not happy with it, then I tried to do something. That's what started. I hope I will be able to. Okay, so then you see here that the error equation itself or the previous equations xn plus 1 by xn minus xn less than or equal to 3 and limit goes to n goes to 3. That's what they try to find. So there itself he realized the Patra has changed the definition. If you are able to find, so actually this q and r, q means it is a quotient. That's why xn plus 1 minus x star by xn minus x star. This quotient is coming. That's why it's called the q order of convergence. So if you can get this equation, so then you can say that your iterative method is converges with at least the speed of p. Convergence of p. So and you can see that the earlier equation is same as this. You see here, this, but we can write as beta raised to p raised to n. How then you can do it? Provided xn minus x star is strictly less than 1. Okay, so if it is less than 1, see you keep on apply that. Xn minus x star raised to p is now xn minus 1 minus x star raised to p all raised to p. So keep on doing that. At the end you will get x1 minus or x0 minus x star raised to p raised to n. So you take log on that and raise e raised to log of something, you will get this. And beta is nothing but so beta raised to p raised to n. If you are able to get this is also called the they call it R order, means ratio. Root. It's not a root. It's root order. Both these things they have proved something on the equality of this. So that's all the point. Okay, but there is again you have noticed one thing. What was the problem there? All this equation involved unknown. You are trying to find extra, and you don't know extra. Then still you are saying that you are going to equal this. How you are going to compute the error between them? We can't do that. So then they come up with another computational order of convergence. That means log of xn plus 1 minus x star minus xn minus x star divided by this. So they call it this computational order of convergence. This order also has a problem. This equation involved unknown. The one what you are trying to find is x star, and it is your definition involved there. So that is therefore they come up with another measure that is called approximate computational order of convergence. So you have it is defined the instead of x star is replaced with the difference between the 4 previous equations. Okay. So you come up with this, but on this measure there is again a problem because this required 4 previous iterations, and very often what will happen when you have the iterations when you do it, initially it may oscillate very fast. If it is oscillate very fast, this is going to give you a very different, or if the convergence is very slow, then also this will not give you the required order. So therefore it is always better to use the previous order that was used. Many people work with this. Work with this. So now we have seen so many ways to characterize the order of convergence of the measure. And I will show you somewhere, but this is not a conclusive thing because you may find the method with the same order of convergence. Then again you don't know how to identify it. So then we start thinking in a different way. Can I visualize something? Of course, visual appeal is always better than an abstract thing. So therefore people come up with another way of analyzing an iterative method that is called basin of attractions. So basin of attraction is if you find suppose you have a rational function from C, complex numbers to complex numbers. You start with the point n. For example, if you consider f of x with this is another area, very interesting area to study other than not only for the iterative methods, other methods also. For example, you consider f of x is x squared. Then you can f square, f cube, etc. if you write. Okay. And you start with any x strictly less than 1. What will happen? It will go back to 0. But if you take any x greater than 1, it will go to infinity. So that's what is happening. So this another area of completely is called functional equations. So recently you can see that but there is a square has no square root. There is a paper if you want, you can just square has no square root. This Rajaram put in ISI and one of our students who means if you consider the function z square, you cannot find any function whose square is going to be z square. Okay, so there's a square has no square root. It's a nice area of study. Let's say functional equations. But we are using that some of the ideas from there. And what is say that you start this so if you start at a point and take its iteration and keep on going there. Okay, of course, if there was a board, I would have shown something nicely. Of course, I'll show you something later on. So, and all those points called its origin, where we start go. For example, if you take half, f of x is x squared. If you take f square, etc., half, this is 1 by 4, 1 by x square, etc., you get the equals. So like that you get it. So then we define some of the points. This not belongs to C is a fixed point. Of course, f of z naught, and it is a periodic point. Means the point is not a fixed point, but after some stage, that is going to be a fixed point. If you start with something, after some time, it is going to become a fixed point. So you can play with this by taking 1 minus x for functions. So then you play with it, you can see that. Okay. Of course, I don't have that much time. So then, a periodic point is a point such that r is to b of z naught is going to be z naught. After some stage p, it is going to be a fixed point. So it is called a periodic point. So then also you can call this fixed point, you can call as an attractor if the derivative at that point is modulus of that is going to be strictly less than 1, and it is called a super attractor if derivative at that point is going to be 0. And this is called a repulsor if derivative of the function is to be greater than 1. And it is parabolic if it is equal to 1. So then, what is called the basin of attraction? So that means you have an iterative functions, you have already seen so many iterative methods. You take a functions, if you want to apply a particular problem, and you collect all those points. If suppose alpha is the root of the equation, f of x is 0, so you know one of the root, you take something. But then you start with any point, and if it is going to converge to that point, you call that this attraction. Then you collect the set of all points. If you start from that, it will converge. So then that point we call it adversation. And complement of that point, that means if you start with that point, you will not converge. So that's called Julius set. So here also you can see that those who are physics or somebody is working in fluid dynamics, etc., very often they come up with a problem. They start with the method, and if you start with this point, it is not converging, but if I start with this point, it will converge. So that's one of their problems. But I don't know whether they ever ask you to see why it is happening. Okay, so this so once you have these two methods, so that is defined as Pato set and Julia set, I'll just show you how it will work. For example, let us consider two of the iterative methods, a little complicated. So it is Pythagoras method and it is Euler-Lenstra method. So the first one is called Pythagoras method and the other one is the second one, that's called Euler's method. I want to study the Pato set and Julia set of these two iterative functions. So how to study that? I will take a simple equation f of x is zn minus 1. F of z is zn minus 1 is complex. Of course, okay, I will show you this. This can be done in complex field and real field. Now, of course, recently one of the work maybe will communicate next week. So we even do in 3-dimensional way of study. Let's come here. Okay, so if you look at this equation, what are the solutions? Solutions is e raised to 2 k by n where k is 2. So now to show this, I'll just consider only 3 cases. N is 2, 3. So what we will do, we take a rectangle minus 2 to minus 2 2. You can see that all the root of that equation is inside that. Then you divide it into 401 into 400 grid points. Each point is the point 6 not by 1. So you have some 16,000 some points will be there. Okay. So once you have this point, what I will do, I will apply the equations to this previous equation. Zn minus 1. And what I will do that if error between the iterates is the moment is less than 10 raised to minus 8, I will say it is converging to that point. Otherwise, and within 40 iteration only for this messy figure which is going to come. within 40 iterations. If it is not converging, I'll assume it is not going to converge. Okay, so then we collect what we will do if we have a root. If we, for example, n is 2, there is 2 root, n is 3, there is 3 root, n is 4, there is 4 roots. So each root you give one color. Okay. And if the point start with it is converged to that root, you give that point a particular color. If you start with the other point, if it is color. And if it is not converging, we will give them black. You see the mathematicians can also do nice paintings. You see, but if you ask me to paint this, I can't do it. It is mathematical because of the study that method. What I did, I put it into this. For n is 2 case, you can see that it is Newton's method. Of course, the simple method I applied. Newton's method is xn plus 1 is xn minus f dash of xn equals to f of xn. Just a simple one. You put it for these equations. And in these 2 cases, there are 2 roots. You can see that it's almost, if you start any point from the left of 0, it will converge to one of the root thing. There is no point, it's not converged. Whereas, in these 3 cases, there in the middle there is some point, you can see it's black. That means if you start any point from that area, no, it is not going to converge at all. Okay. So, n is small. You can see there the dark spots are increased. Many places there. If you start any point from there, you will not converge at all. Okay. So, if you look at Witt-Jacobs method, of course you can see that the figure will become very nice. But the problem you see here, dark spot is increased. That means there are plenty of points. It will not converge at all. If you start any point from there, it is not going to converge to any of the roots. Okay. So now you can realize that if you look at the iterative method, it is not just looking at its order of convergence. That's the problem where precisely when the computation people start with a point, no, it's not converging, why it is converging. So if you look at the Euler-Streicher's method, it's even, but I think I didn't put the calculate the percentage of points here, but here you can see that in these 2 cases also there are points where it will not converge. Okay. And as the complexities or the order is high, naturally there will be more points. The problem will not converge because there are many roots for those points. So this is another way. So now we have already seen one way is looking at the order of convergence of a method. The order is high means it will converge fast. But that doesn't mean that method is going to be good because if you start with a point, it may not converge. So then you try to analyze something geometrically to see whether it is. If you know that the method is blindly start with any point, it will converge, then you are little more happier than the speed. Because otherwise you will spend all your time by starting with a point, it's not converging. So you will get it. But still I am not happy. If these 2 is not enough, then we have another method. So that is called information efficiency of an iterative method. That is, of course, people who are working with this area, any area of mathematics, in fact, they will always try to identify some problems and try to fix it by detailing something. It's called information. That means if the order is P and you need not to find that, not to apply that iterative method, you need a evaluation of the functions or evaluations or its derivatives. And if the number of functions evaluation or the derivative evaluation is more, you will spend a lot of time to compute it. So if it is this ratio, it is called information efficiency. And you also come up with efficiency index, that is rho raised to 1 by p raised to 1 by k, where p is the order of convergence and k is the total number of derivatives or functions where each iteration is required. Okay. So next question we want to ask is, if you have a iterative function, then you will start asking the question whether this method will converge. Of course, converge means in a domain, it is starting with a domain, whether it will converge or how to classify the convergence. If you have a global convergence, there are 3 types of convergence. So first is called global. That means it will have a unique solution in anywhere. So, but so this if you are studying the global convergence, normally you are studying the convergence using the iterative function. So the iterative method converges regardless of the initial points in the domain. So, but this is again, you can see that if you are looking at the linear case, you know the Picard's methods, it is always converges with, you put some condition, if sort of conditions, then you know that it is going to converge. But in the case of non-linear, you don't have such freedom. You don't have it. You cannot have a, you cannot even expect a global convergence. If you start with any point, it will not converge at all. Okay. So the almost in the case of non-linear equation, the global convergence is, you can't even look at it. Then another way is looking at the local convergence. So local convergence analysis is we assume the conditions on the iterative function and use the information around a solution in order to study this. Typically, we assume that the solution is existing in a neighborhood, in a very small neighborhood, and the basic idea used here is Taylor series expansion. So, of course, I have to do that. So, what they do is they will expand the given equations using Taylor series, then plug it into it. I will show you that on one of the slides. So, then they try to get that earlier we used that error equations. So they get error equation for the method, and then they say this is going to be order. Okay, so another one is semi-local convergence. This is we picked up very recent, means last year, maybe up to maybe up to 2000 or 2001. Mainly I was working with this. Maybe we will have hundreds of papers in published in the semi-local convergence analysis. So here actually we are assuming the conditions on the initial point. So basically we do we assume, we are not assuming anything about the solution. We assume some conditions on the initial point. And the analysis also is not, even though you are working in a Banach space, we are not going to analyze that. What we try to do is we try to find a majorized pattern sequence, a sequence, a real sequence. If you know the sequences very well, still you can play. Only then you do certain sort of analysis and you get a bounded sequence. That sequence is called a majorizing sequence. And sometimes it is recursive things, and then you study that majorizing sequence and find the condition under which it will converge. Using that, we will get the convergence and some estimate for that. Okay. But the main problem with semi-local convergence is that it doesn't give the order of convergence. It gives the method convergence, but you can't give what is the order of convergence. So in fact, this we started with the basic idea. When we were looking at it, we look at this, all those Newton's method or various other methods I have shown. You can see that it actually it involves the derivative, first derivative of the function of this. Okay, almost all the methods, first derivatives. But in order to prove that, for example, if the order of the convergence 5, you need 6 times the operator should be differentiable. Then only you can prove that. So you can see the error equations. So P and the order of P n plus 1. That P n plus 1, then if you want to get, you need the function to be differentiable as many times as possible. So that means that practically if you have a theory, but that you cannot apply to the problems if it is not very small. So we were looking at those problems because it's a natural question arising in mind. Because you are you sequence have only the first order derivative, and you are saying if you want to prove it must so many times it is differentiable. So we start thinking, can I do, at least can I prove that the method will converge without using higher order methods? If it is there, I can apply it to the problem. So that was it. So we come up with a nice way of doing things related. Of course, now we stop it, and remaining lot of other papers we worked, but we are not interested in publishing, so it has come as a book. 4 plus another 4, 8 volumes. 8 volumes is coming after 2 months, maybe in March. So there is a way, because after some time we will fed up with it. Of course, we don't want to publish for anything, so we stop it. Then we stop. So this is about semi-local convergence. But today I'm going to now, okay, so next we just compare these few methods for its efficiency index and information index, and we can show that that also is not going to give you any conclusive things which one you have to use. Okay, so we are going to compare this few methods. First method is the reports method. Of course, this method already we have to publish in somewhere. So then another method is new Wasim's method. I think this is recently appeared in demo analysis. This is Newton's Gauss method. It's already you have seen in the first one of the slide earlier. Then, yeah, so Newton's Gauss method. And some of the extensions, of course, this is another way. What people do once you have a method of order, say something, one Newton step extra if you put, you can get almost increase the order of convergence. That's called 4th order, 6th order, etc. You can get it. So, yeah, then Zia has considered a method of equations like this. So, of course, all this method, whatever I am showing here, these are all, each one is already appeared in this paper with something. Just, of course, now I am doing something else. So these are just to see that all this method, you can see that only first derivative is appeared in the method, but the existing theorems, if you want to prove this, if the 6th order means minimum 7 times differentiable, that condition is assumed to not be related. Because that we already ruled out, we have avoided with that we can prove it. Okay, so this is what I am saying. If you look at this, it has order of convergence. You can see that if you look at the 6th order method, the last two of them, so that I think the last one and the 6th from below. Both of them have 6th order, and if you look at its efficiency index is same, and its information efficiency also same. So then how you are going to decide, because this will not help you. So order is also same, a number of functions, but whereas if you look at the third one, means 4th one, order is 6, but you know you need to compute it, you have to 7 functions you have to compute. So naturally that you can exclude because you need more computation. So you will not use it. But other things, so this is the problem why people are going into now the basin of attraction studies, because this also will not do it. The order is same, or if you compute everything is doing the same, you cannot decide it. So therefore you look for the basin of attractions and see the, you apply the method to a non-function and see how much percentage of the point is not going to converge. So then you can decide this. Okay, so let us now come very rigorously to a method. So to see how we are thinking in a different way to prove this. So let us consider this is I think it's one of my paper. I don't I do it between when I switch over period, the first work I do alone. So once I get the results in a particular area, then I am happy as I can work on that. Then only I give to students with that. So first I want to try to other people. Normally I am not publishing daily because it affects the students, need for them to stay. Then only I improve it. So that's why this was not a target. Okay, so you consider a single method in order to do this. So this is, I think it is 2012 they have proved this method is of order 4. But the thing is that they need this 5 times it should be differentiable in order to prove this. what they do is, they, as I told you, they use the Taylor expansion in order to get the convergence order. And they need 5 times differentiable. So this is what they do. The basic idea, all these papers, even now also, many methods are coming. Basically what they do, they expand f of x like this, as a Taylor expansion. Of course, ANs are going to be 1 by I factor into f dash of x star inverse into f dash of x, and then f dash also is there. Whatever things is there, everything you expand in you see Taylor expansion and plug into the equation. Okay, so if it's a denominator, for example, if you look at Newton's method, f of x divided by f dash of x is there. So you can see that f dash of x, f dash of x square will get cancelled, and the denominator is I plus 2x square etc. times will be there. You take it into the numerator using binomial expansion and split it, and you expand it, and you see that if you want to get the order say 3, Newton's method is order 2. So in that case, all the terms mean power or below is going to get cancelled. So now you realize that how they are getting the method. What they do is, they have an iterative method, they will sit down and play with it, and you expand all the Taylor series or put it in various ways, and see if I want an order 4 or 5, and look at all the other terms, its coefficients will have some constant, you put it in the method, and see that constant is equal to 0. Okay. So that's the way they people create the new methods. So basic idea, they always use Taylor expansion and expand it and put it and rearrange all the things and say if I want a particular order, so now people come with 15th order, 16th order, etc. And what they do is previous days you get a set of equations all the time. Okay. But the problem is that you have a 15th order method and you need the function to be 16 times differentiable. That is very smooth function. You can't expect such a functions in your natural way of doing it. So, the major concern in earlier studies is assumptions of f up to the 5th derivative, and it is used because it is clear. So, the natural question immediately comes to your mind: can I prove convergence without using errors? So, that is where you start thinking. I am telling you because when you see a problem, ask questions, ask many questions as possible. So then look at it, why people are getting this order. If you study the paper, yes, read this book, all the theorems are there and you never ask why this theorem, why can I prove it some other way. Even a very well-known theorem, always when you see, try to see whether I can prove it some other way or why I am getting this. Because all the problem is because it's Taylor's theorem. So start, redo it. Can I do it without Taylor's theorem? Okay, so for example, if you look at these equations, if you want to use the method here, it is 5 times differentiable. Even for the derivative itself is unbounded. So that means you cannot use that method to solve this equation. F of x is 0, this is 2%. But actually you can do it. That's what is happening. Because you can see the examples like this. The higher order derivative does not exist. And the method, if you look at, if anybody is given method without the, if he doesn't know anything about the convergence, he can very well apply the method because method from first derivative is required. This equation also for 1 times differentiable. So if you apply the method, definitely he will get a convergence solution, he will get it. But if you go to a mathematician who knows the theory, he will know, he cannot apply because you see the theorem, look at the theorem, it says it must be 5 times differentiable, but this equation is not 5 times differentiable, then how can you apply? But student will say, no, I applied, I got the answer. Yes, it's true, you got the answer. So that means there is something wrong. But it's nothing wrong in the theory. The theory is, we look at only one way. We have to try to find it in some other ways. So this other problems of the earlier is that there is, you can see that they will say xn plus 1 minus x star is something plus and then order of this term is there. That means you don't have an error estimate. You don't know, just order of that only you know. You don't have an error estimate for that. So why we want an error estimate? Because if you know the nth derivative is some constant times something, if you know the error, so then you can always using that to restrict the number of iterations required. You have to stop your iterations. So if there is an error estimate, then only you can do it. But on this theory, whatever theory you see, they will say this method is okay, this of fifth order, sixth order, whatever the order is there, but there is no error estimate is given. So that is one thing. And there is no information on the uniqueness. So if you look at it, if you use various series, you cannot know anything about the uniqueness. Okay, these are all the problems. So, and of course, all these methods actually, if you look at it, is in R. So what we are doing is we modified it into Banach space. Of course, inverse space there is a problem. So some of them we cannot do it. Because Banach space, especially Banach space, the Banach algebra is there. We need that. Okay, so and of course, semi-local convergence was not provided. So what we did is, we proved the same convergence order, but we need to assume that the functions differential at the most 2 times only is required. In all those methods which are shown, we have proved it with 2 times differential is enough, and we can use a Taylor expansion, and of course we can modify it into higher order methods. So these 2 methods we extended. You can see that the last step we just to modify, you can increase the order of convergence, but naturally it increases the computational cost. Okay, now look at these 2 methods. Again, these 2 methods, if you use a Bayesian of attraction, apply those 2 methods to this equation. Because this is real. So it has first one has 3 roots, second one has 4 roots. So you see, you will get the if you apply the first method, you get again nice pictures. So you can see that there are so many places dark spots are there. So if you start any point from there, it will not converge. Okay. Whereas if you start from the other points, it will converge to one of the root. Okay. So this is for the 6th order. When you here again see that the order is increased and the number of non-converging points decreased. Okay, if you look at the next example, there are 4 roots, so 4 color plus black. So you can see that dark spots are coming there. Of course, this is even it looks much better if you increase number of iterations. You must have a computing capacity. 400 into 400 except 16,000 points are there. So it takes some 2-3 minutes. But if you increase the number of points, you can get much better figures. Very nice pictures are there. Of course, and if you look at the 3-dimensional way of looking at it, if you have an equation, so it's very nice artistic things you can see. It's not just maths, which is much more interesting. Okay, so if you look at those 2 methods, you can see that this order is 6. The first one required only 4 functional evaluations, second one required 5 evaluations. Even the order is increased, the computation of course is increased. So therefore, in this case, you can even prefer one order. Okay, so now we can just look at real mathematics. So if you want to prove something, so you need to assume something. Okay, so what are the assumptions? So instead of assuming it is 6 or 7 times differentiable, we just assume that its first derivative satisfies a Lipschitz condition, and second derivative is bounded. That will be and the second derivative also satisfies a Lipschitz condition. And the first equation, so if you y minus x is y minus x star, so of course there is a mistake. In the 510 it is y minus x star, not x. So I'm sorry, it is correct. Okay. So in the first equation, so you see the left side, suppose the left side is less than 1. Then you have the Banach lemma, I don't know whether, how many of you are MESC students here? MESC MES? So Banach lemma, you must be knowing it. What it says is the norm of an operator is strictly less than 1, then I minus t inverse exists and norm of I minus t inverse is less than 1 by 1 minus 1. So the basic idea we are using, the first one, if you expand it, what you are getting, f dash of x star inverse y minus I, that is less than 1. Okay, so that means I minus that, I minus, if you take this 523 will come. Yes, so this, I just stress this because when you learn MSc, even I was saying, what is this vernacular mass? They say, no, something is less than 1 minus this, less than 1 by. We didn't find anything very interesting there. But you see here, how we apply it is when you look at it, actually I want to see, I want to f dash of y equals for any y into f dash of some element. I should do power. That's what I want to do. But I don't have it. What I did, I used the Lipschitz on the first one. The moment that is less than 1, then immediately, yes, I have this Banach lemma is there, Banach is there. So get it, converts. So that's where you have to learn. You have to look at it, how we can apply it. Various things. So just a simple application of that. And again, so next one, we can get these two things immediately follow. So then we are at the sequence which we have seen earlier at 4.18. So that we will prove that it is going to convert this it is e to r into x1 minus x r raised to 5. Do we know how much time I have? Otherwise, it's already given because I don't want to open that. Okay, then so the proof is given there. If I click there, proof will come right up there. So it's like this. Okay, so the basic idea is, you see there some functions are come. How do we do? We just take x1 minus x star and do certain way of adjusting it and bound it. Okay, and that bound is finally going to depending on some functions like this. Okay, so I need to, what are these I need if I sequence, I want to say this convert this, I want to show that it's going to be in some border around radius, around x naught. The moment it's there, all the x's are going to be in a border of some radius r, then you know that in a Banach space, it must convert, it's a bounded Cauchy sequence. So it's going to be bounded. So I want to find what will be my radius. So I do all those manipulations and get this bounded by functions of wherever t is there, it is xm minus x star. So that's where it is going to come. So then I want to show that this will have a root. How to put it? I apply t square, h2 and t is d1 t square and show that it was a root. That solution is going to be my radius. So that's why I fix it. Radius and then again is going to do the same sort of manipulations. And I get a radius, and then I will say, okay, so three wires were there for 5 and 6. So series is 6-1 proof, probably I can show. So it's a single proof. So means single proof is depending on the this. So basic idea is expand. First you start with x1 minus x star, and you see the mean value here. I'm not using very serious results from functionals. Only you can see that f of z minus x star. You apply mean value theorem and get in the form. Then do certain adjustment, and you can see that it's going to be order. Then we also prove uniqueness of the research in a world. Yeah, so all these methods, semi-local, we have proved recent ones. So I think maybe this Spotify is reaching your lunchtime speech. I don't want maybe more hungry. So most of many of the unpublished papers, collections are in this for those, but don't buy this book. It's very expensive. Each one is around 20,000. So another one is this is for the model is going to come again. So
Is it available in online?
it's available. 18,000. It's $230. It's an American publication, so you can't understand. Cheaper than each one is I think $230. So they give us a complimentary book. That's all. Although some of the references are used, so usually I avoid my own references. So you may not find many here. Maybe only one is there. Yeah, 2 or 3 a day in mind. want to see my work. So these are the references used. Many of them are my collaborators, some of them are collaborators. Any questions?
Any questions from the audience?
Almost students are choosing this type of areas after completing plus 2. Pure and applied mathematics students are working under this area. Actually, sir, I have one question. Can you explain some real application for that fixed point? Some real life applications, or why we are using that fixed point functions? Or
It's not like fixed point. I told you, I think I was about to say the only mathematician who got a Nobel Prize in mathematics. It is your CT scan. All of you are about CT scan. You know, it's happened actually in 1929. John Radon has developed something called Radon transform. Okay? So there is an institute called Re-accredited. Radon Institute of Applied Maths and Computation. I was there. It is in Austria. I was in 2008 for a month. I was working with a professor there. You see, what Radon is did, he has find a physics people must be Radon transform, like Fourier transform, etc. Nobody ever bothered about it. And it's 1964 when people start working on X-rays and MRI scans. So they were struggling. And then suddenly somebody, in 1965, somebody say, oh, what you are doing is Radon done in 1939. They applied, then took it, and then I think 71 or 72 Nobel Prize is given for. Actually, he got a mathematician. He worked with things. That's where the MRI scan is developed. So what is happening is you put magnetic resonance and get all even the X-rays through your body and different shapes, different notation. You collect its logs. Then you try to invert it. So when you transform it, what you are going to get an integral equation of the form a to b a s t dt is y of s. It's a first case equation. First case equation is imposed. Means it doesn't have a solution. So how to do it? That's where so that is where I start working with. So it's like a g of x is y. You want to solve, and it is not 1 1. He is not 1 1. He is not 2. And mostly the practical application operators are so-called compact operators. And compact operators on infinite dimensional Hasse problem, its range cannot be closed. If the range is closed, at least you must be using that linear fix. What do? You project it into the range space, then you can solve it. But if the range itself is not closed, you cannot even project it. So then how to do it? So there, what we used to call regularization techniques. So all these things, even I can convert my imposed equations into this form, because f of x is y, I can write f of x is 0, where f of x is g of x minus y. So that's one of the examples. And it's not that people are still working on various things. Image processing, I am also there. I have students in image processing. There are many papers I am working on that. That is there. So not only that, 2015, I was in Göttingen University. You know, Göttingen University is famous for, there is near to the university, there is a grave full of Nobel laureates. All the Nobel laureates, there's so many big shots were there. So I was working with Professor Hobson and his student called or something. They expect he also might get Nobel Prize in medicine. What they are doing, see, now the problem with the MRI scan itself, you need almost half an hour at light like this. So if you are in a dangerous situation of emergency, you don't have that much time. So you are trying to find reduced time, and he has developed within 5 minutes. And when I was there, they were shown that you can see your heart is bubbling in your computer.
within 5 minutes. So how they develop, people are saying that what mathematicians are doing, and their job is their group. If medical students are there, they are working, they develop the algorithms in such a way that you get a few slides. Let's say MRI also, if you go to hospitals, you get 14 slides, 23 slides, etc. It is written there. So if you are going for a 14 slides, means just to know something they put it. And the other one you have to lie there for half an 23 slides, 24 slides, etc. How many ways are taken? That's what they are doing. So they are doing. If you want to do in India, you cannot do because we don't have that much of facilities. It's all applied. But you ask me where is the practical, I always say that as a mathematician, I never bother about practical. My pleasure is to solve something. It has its own interesting way of looking at it. More abstract. Even though I don't know some practical things, basically I'm not happy with practical. Theoretically.
Okay, thank you, sir.
Ladies and gentlemen, it is an honor to invite our esteemed speaker, Dr. Santosh George, to join us on stage for a special moment.
Good afternoon all. I am here with immense gratitude as we conclude the first plenary session for mathematics in MESKCON International Conference. This is a proud moment of our department to have our alumni as our resource person in this international conference. His presentation in the heartfelt thanks to Dr. Santosh George sir for his insightful and enriching speech in this session.